Okay, here we go. This is going to be an example on the one item that we haven't done any yet, which is an indeterminate with an applied loading, right? We did one with temperature, we did the second one with support settlement, I think, and now we're going to take the case of the applied load. Let's consider something very, very, very practical and common. There's going to be a little detail. It's not the only way to do it, but I think it should not be too hard for you to follow. Okay, so we're going to consider a beam having three spans, all equal to each other, L, 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 and a uniform load, W. We want to draw the shear and the moment diagram. There's a lot of ways. I mean, there's one. If one has enough expertise, I'm not going to do it, but with enough expertise you can say, this structure, I can see, right, that it's symmetrical. Therefore, I know that these two reactions are equal, right? And these two reactions are equal, so I can take advantage of that and reduce my computation if I want, okay? But we're not going to try to do any tricks here of that nature, because you guys are just getting introduced to this topic, right? This ability to do indeterminate structures. So let's just go and do it standard. First, we look at the structure and we say, okay, how indeterminate is it? Now, don't make the mistake of saying that you can just determine that you can assess the indeterminacy by just looking at the reactions. There was a person in the exam that just said that a certain structure was indeterminate. Yeah, the beam of the third problem was indeterminate because it had a fixed end and a pin support, a roller, so he counted 4 reactions indeterminate. No, that had 4 reactions, but there is a hinge in the middle, and because of that hinge it's not indeterminate, it's statically determinate. So the reactions do not necessarily determine whether the structure is indeterminate or not. There's also, for example, a situation like this, right? That I've shown before. That structure only has 3 reactions, but it's indeterminate to the 3rd degree, because you cannot calculate the moments inside here. You have to open it up. And when you open it up, there's 1, 2, and 3 unknowns that appear there, right? So that structure is indeterminate to the 3rd degree, and it's only got 3 reactions. And a structure with 4 reactions can be determinate also. So it's not the fact that you can just count reactions to identify the degree of indeterminacy. Where did I put this erasing thing? Hold it just a second. Yeah, here it is. Okay. So we have that, right? In this particular instance, there are no hinges. So if I take these 2 reactions off, I can see that that would be a simple beam that is statically determinate. I could also take this off. It would be a simple beam with 2 overhangs. All kinds of different options, right? So here I'm going to choose to take the 2 reactions in the middle as being the redundants. And so this one is going to be x1, and this one is going to be x2, even though I know from the outset that x1 and x2 are going to have to end up being the same because of the symmetry of the situation. This is indeterminate to the 2nd degree. Okay? Notice also something that sometimes confuses some at this stage is that when we draw a beam, okay, we normally take one of the supports to be a pin and all the others a roller. which one is the pin and which one is the rollers, it's a matter of convention, right? It doesn't really matter, because we don't have horizontal forces. All we are saying is that this beam is held against horizontal translation. I mean that because, I will erase it, but had I decided to do this and to take this as the redundance, for example, this one an x1 and this one an x2, right? There would be two rollers left here, but I cannot really draw two rollers because then this structure that I'm showing here would be a train that could run to the right. So I would just turn one of them to a pin, right? So I guess what I'm saying, notice that even though this was a pin, I removed it completely by just giving one unknown. I just simply took the horizontal constraint and put it here. So this would be the way of treating x1 and x2 as being the redundance. The fact that I showed the pin here, it's actually completely arbitrary choice, right? I could go like this and show this one to be the pin. It wouldn't make any difference whatsoever because we have no horizontal forces. This is just a convention to say we know that this thing should not be allowed to slide for the purpose of formality, right? Okay, so I erase the second one and focus on using the first choice. Okay, so this is going to be our structure. So we're going to need what? The x1 equal to 1 sketch, the x2 equal to 1 sketch, and the p sketch, right? Now, that was run really big so you could see it well. Now I'm going to, well, maybe the way to do this is like this, right? Instead of trying to do everything, erasing a lot, let me just go like this, take that off, and say, this is a 1, and this is the x1 equal to 1 sketch, right? You remember the previous one, you've seen it. It's already in front, I mean it's in the video just a little bit before. Just imagine I drew this again, right? So this is the x1 equal to 1 sketch. I can do the x1 equal to 1, x2 equal to 1 without doing anything about the p. I don't even need to know the p to do the x1 equal to 1 and x2 equal to 1 and x3 equal to 1, right? I can just select my redundance and do my sketches. So here's my sketch x1 equal to 1. The statics are trivial, right? This is L, L, and L, so it should be quite obvious that this is 2/3 down and this is 1/3 down, right? Now, if I take this coordinate to the right, starting from this end as x, I can say that my moment here, M1, would be, now it depends, I can choose any sign convention I want, right? I could call that plus 2/3 of x or minus 2/3 of x, anything I want, as long as I'm consistent next time. So I'm going to call it negative 2/3 of x in order to say, okay, something that is producing tension, a compression on the top, I'm going to take positive. So I'm going to take this kind of thing to be positive, okay? This is actually producing bending the other way. If you look at the bubble would be like this, right? And so this is counterclockwise, so this is clockwise. So this is like that, right? I'm saying that moment is negative because it produces tension on the top. That way I just remember for good, right? This is what I'm taking as plus. This is like this. That I'm taking as minus. Okay? Now, there's going to be an issue here. So I'm going to go like this, right? To show that this M1, I could write it, right? That 0 is less than, or you could say this is valid for 0 less than or equal to x, x less than or equal to L, right? Mathematically consistent. It's valid only there. Now I can start from this side. I could start from here, but I think this side is easier, right? So we go here. Let's call this coordinate z. And I think by the same argument, it should be rather obvious, right? That the M1 here is minus 1/3 of z, right? And that is going to be valid all the way for the rest, right? Over here. And if we want to write it mathematically, we would say 0 is less than or equal to z. Z is less than or equal to 2L, right? So that is our x1 equal to 1 sketch. Fine? Okay. I think the x2 equal to 1 sketch, it's rather obvious, but then there's going to be a little bit of thinking, okay? So this is like this. Now we go here. We have a 1 here. These markers are at their last leg here. And I have to venture out to Target or something to get some more. But that's a 1, right? And here is our reaction. And again, from statics, it's obvious that this is 2/3. It's obvious that this is 1/3. And now is where we run into what at first might appear like a complication. It's not. Okay? If we start from here, we can say that the moment m1 here is minus 1/3 of x, right? Now that 1/3 of x, if we use x really, in this case is valid all the way to here, right? So that 1/3 of x is valid from 0 less than x, x less than or equal if you want, 2L, right? And if we start from this side now, with this being z, we have that our m1 here is minus 2/3 of z, right? And it's valid in this part, which is 0 less than or equal to z, z less than or equal to L, right? That's it. We've done our x1 equal to 1 and our x2 equal to 1 sketches. There's a little bit of an issue with this part here. And there is a way to do it without ever having to do what I'm going to do now, which is to start another coordinate here that goes that way, and then describe this as m1 in terms of x, then m1 in terms of, I don't know, n, and then z. So you can have 3 coordinates, okay? That's one way to do it. But I'm going to venture to do it with just these 2 and hope that you will follow what I'm going to do, okay? So I'm erasing up here so I can leave the sketches, and I hope that that room there will be enough for me to illustrate what I'm doing. So let's begin by calculating the hard one, because f11 is just going to be this times itself, right? That's not an issue. And I think it should be obvious, right, that f22 is going to be the same as f11, because this sketch and this sketch are really the same thing, just when you look at it from the back of the board, it looks the same as this one. So f11 is going to be the same as f22. And they don't present any issue, conceptually. But f12 might. So let's go and say we want to calculate f12. So instead of writing divided by EI, I'm going to put the EI on the left, and I want to see what f12 is. So it's sketch 1 times sketch 2, right? Or sketch 2 times sketch 1, same thing. So from 0 to L we have no problem. We say it's the integral from 0 to L of minus 2/3 of x multiplied times minus 1/3 of x dx, right? That's divided by EI, but the EI is here. So that's covered this chunk. All right? They were both valid, because this is valid from 0 to L, and this is valid from 0 to 2L, so that's fine. Now let's do this chunk here, which is also non-controversial. So we say plus the integral. This one is valid here, and this one is valid here. So we can say minus 1/3 of z, right, multiplied times minus 2/3 of z times dz, right? from 0 to L. So we have covered the first L from the left to the right and the last L from the right to the left, right? We're left with this middle space here. Now, that middle space is a little bit tricky if you're not too sure, but I hope you follow me now. I'm going to say that that middle space, what we have to do is just multiply valid equations, right, that cover this region. So what is a valid equation that covers this region in this sketch? Well, the valid equation that covers this region in this sketch is minus 1/3 of x, right? So minus 1/3 of x. That describes what's going on here, right? Minus 1/3 of x is valid. Now what is valid over here? What is valid over here is minus 1/3 of z, right? And then we see that we got a bit of an issue, right? Because we got x and z. So we say, well, how are we going to handle that? Well, we can decide to integrate with x or to integrate with z, either one. And then we're going to have to find the mathematical translation from one to the other. Let's say that I choose x. So I'm going to integrate with x. So I'm going to say dx. And then where does x go to cover this region? X goes from L to 2L, right? So this would be from L to 2L. All right. So far so good. We only have one kind of inconvenient situation, which is that this integral has x and it has z, right? Now look at your sketch. X starts on the left and goes to the right. Did I not draw it? Whoa, that's bad. Well, I see my z over here, but somehow the x escaped my process, right? So here is my x, begins there. My x is here, begins there, right? So x starts here and goes to the right, z starts here and goes to the left, and those are the expressions, right? This has only x, this is only z, but this has x and z. So now we realize that what happens is that if you take this point here, that point has a certain x, right? And it also has a certain z. So it should be obvious that x plus z is 3L, right? Therefore, if we decided to integrate with x, we can just simply say that z is 3L minus x, right? So that's one way to avoid having to do a third coordinate. Then, if we accept that that is true, actually, we have to accept that that is true because it is true, right? Now, I don't have any more room here. So, unfortunately, let's see, I can do something here? Yes. I don't want to erase it because then I'm going to miss the stuff. So what I'm going to do is this. Let's look at this integral. Right? I mean, there is nothing to do that integration and nothing to do that integration. And I hope you guys agree, right? I mean, that's just trivial and trivial, right? Nothing to it. In fact, these two things are the same. So it's just 2 times one of these ones. Okay, so let's look at that one. Not that there's anything to it, but just to show that what we're talking is the integral from L to 2L, right? Of minus 1/3 times minus 1/3 is 1/9. So 1/9, I can take it outside the integral right away. And then we have x, right? And we said that instead of z, we will put 3L minus x, right? 3L's minus x. And then dx. And so that thing right there, it's this, right? All right? So, instead of wasting time and having you look at me doing stuff that doesn't teach anything, just very simple integrals, let me take my time and your time more efficiently to describe the conceptual things one more time. We had a beam, which I had to erase or space, but we have a beam that has 4 supports. I've decided to use the 2 internal ones as my redundants. This is my sketch for the first redundant having a value of 1. This is my sketch for the second redundant having a value of 1. The statics when this redundant is here is that this reaction is 2/3 and this reaction is 1/3. Now, from a mathematical point of view, I just need equations that describe the moment, because that's all we're accounting for, bending. Axials are 0, there are shears, but we know that the contribution of the shear deformations is very small. So we just need mathematical expressions that describe what the moments are everywhere here. So we start by selecting a coordinate x that starts on the left. We take a bubble, we decide on a sign convention, and you agree that we get that m1 is minus 2/3 of x, with x beginning here. We realize that that expression, because of this 1 here, the bubble is only good up to the 1, right? So that expression is only valid from 0 less than x, x less than L, which is this region, right? Then we start on this side. We call this coordinate z running from the support to the left. And again, a simple bubble shows us that the moment here would be minus 1/3 of z, where the minus in both cases is completely arbitrary. I decided to use upward bending, bowing upwards to be negative, bowing downwards to be positive. So this moment is minus 1/3 of z. And if we look, we see that that moment would be valid all the way from here to here, right? So I can write down if I want, just to remind myself or to see it or to make it clear to you guys or for whatever, that this expression is valid from 0 less than or equal to z, z less than or equal to 2L. And so we have covered, and that's all we need, right? We have covered the full domain. We know what the moment is everywhere. We now take a look at our second beam. And in our second beam, we have the same situation, right? There is a 1 kip load here, and we have the beam here, and the reaction here is 1/3. The reaction here is now 2/3. Once again, with the same sign convention, which I must be consistent, I find that my moment m1 here is minus 1/3 of x, but now the region where this is valid is all of this region, right? 0 less than x, x less than 2L, and then from this side with the z, I cover this part with minus 2/3 of z. Now I am doing EI F12, which is sketch 1 times sketch 2, and I find over this region that is minus 2/3 of x times minus 1/3 of x dx from 0 to L. That covered this part. Now I go to here and I see this part, and that is minus 1/3 of z times minus 2/3 of z dz from 0 to L in z, right? Now we're left with this middle portion here. And in this middle portion, in this sketch is described in terms of z, and in this sketch is described in terms of x. So we begin by just writing it down. Minus 1/3 of x, where am I? Yeah, minus 1/3 of x from here, in this region, minus 1/3 of z from this sketch, right? That's the expression. Now we have to decide whether we want to integrate with x or with z. And we said, okay, let's integrate with x. Could have chosen z, but I decided x. If I integrate with x, my integral limit is from 0 to L. I'm sorry, not from 0 to L. From L to 2L to cover this span, right? And then I say, well, okay, but in order to do the integral, I cannot just have x and z, so I need to relate these variables, see what's the connection. I realized by looking at my beam that x plus z is the whole beam, right? Any point, that point right there, has an x, right? And that same point has a z. And when you add the x and the z of that point, you get 3L, no matter what the point. Therefore, x plus z is 3L, therefore z is equal to 3L minus x. And we now are able to go here, and instead of writing z, we write 3L minus x times x, multiply the 2 minus 1/3 and put 1/9, and that's that integral. we perform this integral, and that integral, and we get EI F12. And it turns out that EI times F12 is equal to, let's see, I got it right here. Wait, what am I having? What am I doing? Sorry. It's right here. It's equal to 7/18 of L cubed. Okay? If you'd like, I would if I were you, you can do that integral yourself, this part, convince yourself that you agree, and then if you want, do the other substitution, and don't do it in terms of z, do it in terms of, in terms of x, do it in terms of z. If you were do it in terms of z, actually you would see it looks exactly the same, because x would be 3L minus z, and the thing would look exactly the same, right? So there's no point on doing it because it is the same exactly. So now we have 7/18 of L cubed. Now, to go forward with the other parts, we have to do F11 and F22. In F11 and F22, this issue about having substituting x and L does not arise, right? So we can say EI times F11 is equal to the integral over this part, which is the integral from 0 to L of minus 2/3 of x squared dx, right? That took care of this part, plus the integral from 0 to 2L of the moment here, minus 1/3 of z squared dz, right? And that's it. With the EI here, because the EI was constant. Of course, what would happen if the EI was not constant is that I cannot just say put the EI here, right? I'd have to put it where it belongs, in the denominator. But with that in mind, if you do it, you find, I don't think it's worth, that's again, wasting time with that. It turns out to be 12/27 of L cubed. So that's what EIF11 turns out to be. If you look at the sketches or write the equations, you will find that this is, of course, also equal to EIF22. So really, we've calculated everything there is to calculate with regards to the flexibility, and all we have left is what is delta 1 and what is delta 2, right? So now we need, because remember the flexibility method, right, is F, this is the case without support settlements or temperature, this is load, so this is F plus X, well actually no, wait, for any method is this, right, for any loading, it's just, this is the movement of the redundance due to the actions, the final movement of the redundance. Our final movements of our redundance is 0, so we are working with the case delta is equal to 0, right? So we have this. What we are missing now in this problem is just simply delta 1 and delta 2, little ones, which is the movement at the location of the redundance due to the loads, right? Movements at redundance due to loads. All right? Movement at the redundance due to the loads. We then need the P diagram, right? So I will erase here, and I'm going to stop the video to shorten the size of the files and start it again.